Welcome to the deep dive. Today, we are taking a monumental leap into the interconnected revolutions that are quietly but fundamentally reshaping the physical world all around us.
That's right.
We're talking about how software, AI, and distributed power are remaking, well, everything. From the invisible cell network you use every day to the future of your car and the entire energy grid that has to power it all.
And our mission today is really synthesis, because these aren't just separate technical shifts. We're blending sources that cover these massive global trends, the rise of software-defined vehicles, the spectrum needs for 6G,
Huge stuff.
huge. And we're looking at them right alongside these very specific local infrastructure projects, things like a multifunctional smart hub being built in, say, Refugio County, Texas.
Right.
The challenge isn't just absorbing the tech, it's connecting that digital strategy to the physical reality on the ground.
And that reality creates this massive paradox. To support this coming surge in digital intelligence, all the AI, all the data processing, we need these monumental shifts in our physical infrastructure, especially around power and connectivity. So if AI is the brain, then the wires, the towers, the grid, they're the nervous system, and they are really struggling under the load. We have to figure this out.
We do.
Okay, let's unpack this, maybe starting with that unseen digital backbone.
Let's start with telecom. It's going through this necessary but pretty painful divorce from its hardware-centric past.
Right.
The core revolution is this move toward software-centric, programmable networks. 5G evolution isn't a destination. It's this continuous flux that demands just extreme agility from the carriers.
Okay, so if agility is the goal, what's the biggest roadblock? What's standing in the way inside these big carrier systems?
That roadblock is defined by BSOSS, Business Support Systems and Operations Support Systems.
Okay.
Think of it like the massive concrete ERP system of the phone company. It handles everything from billing to network provisioning.
So it's the old brain of the operation.
Exactly. And because these systems are monolithic, the painful truth is that bringing in one small software change, it often means you have to retest everything,
Wow.
the entire stack. It makes any change incredibly time-consuming and, of course, expensive.
That sounds less like agility and more like trying to turn an aircraft carrier on a dime.
It is. It's exactly that.
So how does the industry solve for that kind of rigidity?
The industry fix is something called the Open Digital Architecture, or ODA. ODA is essentially a blueprint for modernization.
A blueprint.
It shifts away from those monolithic blocks to standardized modular components. It lets them break apart those old systems and build the agile, scalable environments they need to finally become, true tech companies instead of just telcos.
And this is where AI becomes, I guess, completely non-negotiable, especially for just managing costs, right? You can't just over-provision everything anymore.
Precisely. Take network planning. AI models can look at historical data, current trends, and forecast the exact location and timing of peak demand.
So you know where the next concert or big game is going to be.
Exactly. And that insight fundamentally shifts your network build-out from expensive, generalized over-provisioning to a much leaner, targeted investment. It minimizes that massive CapEx.
And that intelligence must also allow for automation in services that used to be really static and expensive. I'm thinking about something like network slicing.
Absolutely. Setting up and tearing down complex network slices, reserving bandwidth and latency for specific customers, that used to involve a lot of manual overhead.
A lot of engineers in a room.
A lot of engineers. AI fully automates this, and the result is that operators can offer these customizable slices on demand at good price points, something that was technically possible before, but just not economically feasible.
So when we look at actually deploying these new systems, the move to Open RAN, the disaggregated radio access network, that's key, right? Especially in brownfield networks, the ones that already exist.
It's key, but it's also complex.
Because you're bringing in a bunch of different vendors.
You are, and complexity is the enemy of cost and speed. That's why we're seeing a very cautious approach. A lot of operators, even while they embrace the Open RAN idea, they're initially minimizing the number of vendors.
To reduce the variables.
Exactly. Because the more vendors you have, the greater the testing burden. That means more risk, more cost, more time. It's a very slow transition away from that traditional vendor lock-in.
So once the network is disaggregated, the job isn't done. You then need the intelligence to manage all those moving pieces.
Correct. The next crucial step is deploying the RAN Intelligent Controller, or RIC, and its apps, the XRAPs.
Okay.
Think of these as the smart apps that live on the network edge. They provide that real-time optimization doing things like steering traffic away from congested areas or, critically, reducing energy consumption on base stations.
And I have to assume that with all this complexity, AI is just as crucial for securing these networks.
It's not just crucial, it's essential. I mean, the
Yep.
sheer scale of 5G makes traditional security totally inadequate. The threat landscape is just too dynamic.
The old signature-based stuff doesn't work.
It just drowns security teams in false positives. You need AI-based intrusion detection systems because they can learn and evolve with the threat patterns. They're just so much more accurate in a system that's always morphing.
Okay, let's transition from the communications backbone to the moving data center. This is where it gets really interesting for me, how software and hardware are changing an entire industry, mobility.
Yeah, we're moving way beyond just electric cars. The vehicle is rapidly becoming a software-defined product. Our sources show a, frankly, startling 74% of automotive executives believe that by 2035, vehicles will be predominantly software-defined and AI-powered.
And the really big takeaway for manufacturers is that brand identity itself is shifting. It's moving from the engine to the digital experience.
That's it, exactly. An overwhelming 75% of those execs say the software-defined experience will be the core of brand value by 2035.
Wow.
It just completely supersedes traditional things like horsepower or interior design.
But the infrastructure required to power that software it's terrifyingly dense.
When we talk about data volume, what kind of numbers are we talking about?
Staggering amounts. An autonomous vehicle, driven an average distance, can generate up to 4,000 gigabytes of data
Per day.
per day. This requires massive onboard compute power, and that data is the foundation for future value. Personalization, new services, AI insights for the driver.
To handle that kind of power and data, the hardware has to evolve just as quickly. So what's the underlying tech that's enabling this new class of EV performance?
It really requires a jump in efficiency. So we're seeing the adoption of 800-volt battery architecture up from 400. This is accelerating the use of silicon carbide, or SUNO power modules.
And Sonosine is just much more efficient.
Much more. It significantly reduces energy loss, which means better range and faster charging. And the competitive dynamic here is fascinating. Chinese OEMs are leading in vertical integration. They're controlling the supply chain right down to the semiconductor level.
Giving them a huge advantage in speed and cost.
A distinct advantage, yeah. But that mobile data center doesn't operate in a vacuum, right? It has to talk to the outside world, especially for safety.
That's where V2X vehicle-to-everything connectivity comes in. It uses a specific spectrum band, and it's crucial for safety applications, letting the car talk to traffic lights, the road, other cars.
And what are the goals for that rollout?
They're highly ambitious. The U.S. goal is V2X capability at 75% of signalized intersections in the top 75 metro areas by somewhere between 2032 and 2036.
Right.
That requires a huge nationwide investment.
And even smaller devices like e-bikes and scooters are part of this whole connectivity challenge.
Indeed. Look at light electric vehicles, LEVs. They rely on microcontrollers, power management units, traction inverters, usually at lower voltages.
Right.
And why this matters is because efficient component selection is absolutely critical. Every fraction of energy you save directly translates into more range and better performance. It's all about maximizing efficiency.
So all these digital demands, AI, connectivity, EVs, they're all converging on what might be the single biggest infrastructure challenge we have today.
Power.
Power. The data center load alone is alarming.
It's the existential constraint on the entire AI boom. Global data center electricity consumption is projected to double between 2022 and 2026.
Double.
Double. Power supply isn't a footnote anymore. It is the primary bottleneck on global digital expansion. The grid has to become fundamentally more flexible.
And that's where the virtual power plant, the VPP, comes in. This is a concept I think everyone really needs to understand.
Absolutely. A VPP isn't a physical power plant. It's an aggregation of distributed energy resources, or DARs.
So things in my home.
Things in your home. Smart thermostats, home batteries, EV chargers, even commercial building HVAC systems. They're all connected by software and managed by an operator to act like a single, flexible alternative to a traditional power plant.
So why should a utility or, a homeowner care? What's the real benefit here?
The benefit is huge. Resource adequacy and affordability. VPPs defer massive capital expenditure on new power plants and transmission lines. If you can aggregate home batteries to drop demand for an hour during a heat wave, you might have just avoided building a $100 million peaking plant.
Can you give us a real-world example of how that works for a customer?
Sure. Look at Holy Cross Energy in Colorado. They enroll customer batteries in their VPP. The customer gets the battery with no money down, pays HCE back over 10 years at 0% interest.
Okay.
And that cost is often offset by energy credits they earn for participating. In return, HCE gets to briefly control that device to help the grid. It's a win-win.
And it's not just batteries. We're seeing behavioral control have a huge impact too.
A massive
Yeah.
impact. Arizona Public Service's Cool Rewards program has over 90,000 smart thermostats. During peak events, they can consistently deliver over 100 megawatts of load shed.
100 megawatts.
100 megawatts of demand that just vanishes from the grid purely through software control.
So beyond flexibility, battery energy storage systems, ES, are also key for resilience, especially for things like microgrids.
Right. Microgrids are localized grids that can operate on their own during a wider outage. BES is a cornerstone because it provides that instant response for critical facilities, hospitals, data centers, to keep the lights on.
And even for just monitoring the grid, we need better backup power.
Correct. For smart grid devices, battery power stations are replacing fossil fuel generators. And this is a huge environmental win because those small generators can be shockingly polluting.
How polluting.
One can emit as much carbon monoxide per hour as 450 cars. So the shift to batteries is essential.
Now, we mentioned the constraint of power, but what about the constraint of heat? Inside all these dense data centers.
Thermal control is absolutely fundamental. If you can't get the heat out, you can't run the chips. And a key technology here is something called thermal metamaterials. These are basically artificial structures designed to manipulate heat flow. They can act like heat cloaks or directional heat shifters. This concept, it's been around for a while, but it's vital now for managing the dense heat from AI compute.
This entire discussion so far has focused on centralized control, utility scale, carrier scale. Let's pivot now to a completely different model for scaling all this infrastructure, decentralization.
Right. We're entering the world of DePIN, Decentralized Physical Infrastructure Networks.
DePIN.
The idea is simple. Instead of centralizing, you use a decentralized cryptographic architecture to build physical infrastructure that's, more efficient, more resilient, and more performant.
So how do they actually fund and manage the physical parts of it?
That's the core of the model. DePINs use crowdsourced capital and labor. People deploy hardware, a sensor, a wireless hotspot, and in return, they're incentivized with transparent token rewards. And crucially, it all uses on-chain settlement as a single source of truth.
Okay, give us a concrete example. What's a DePIN that's deploying physical infrastructure right now?
The clearest one is GeoNet, a global geolocation network. It relies on physical GNSS reference stations, they call them miners, deployed by individuals
All over the world.
all over the world. These miners generate high-precision geolocation data in exchange for tokens. The system uses a consensus protocol that combines proof of stake with geospatial data, ensuring the measurements stored on the blockchain are verifiable and authentic. It creates trusted, real-time data from thousands of autonomous points.
So it's about crowdsourcing trust and connectivity. What are some other uses for this model?
Well, you see it in wireless coverage, where networks like Helium Mobile offload traffic onto community-built hotspots. You also see it in compute marketplaces that leverage latent capacity on people's machines. The goal is always the same: lower prices and greater coverage by incentivizing individuals to solve these problems locally.
So let's tie this all together. We have these two fundamentally different philosophies running in parallel here. That's the core synthesis, I think. The common thread across mobility, power, and connectivity is this struggle to manage complexity, scale data, and ensure resilience. And we are simultaneously seeing these highly controlled top-down models, the VPPs, the centralized telcos, and these radically decentralized bottom-up models, the DePINs.
Both trying to build the same infrastructure.
Exactly. But from completely different architectural standpoints.
And that tension leads us to a final provocative thought for you to consider. In the centralized world of telecommunications, we noted this data paradox. They generate tons of data, but it often has quality issues or it's not trusted enough for full autonomy. Meanwhile, the decentralized world of DePIN is built specifically to create trusted, verifiable, secure data on-chain. So the question is, how will the increasing mission-critical need for verified data integrity ultimately force a convergence, or maybe a conflict, between these two fundamentally different philosophies as they race to define the future of our physical world?